Good afternoon. Let's start off. Alicia, how are you? Eh, okay, good afternoon, students. Hope I'm clear. Okay, we were able to introduce radioactivity yesterday, and we clearly defined what radioactivity means. So today, I'm just going to focus on the differences between the radiations emitted. One of the radiations we talked about yesterday was a beta particle, gamma rays, and alpha particles. We want to see clearly what distinguishes between a beta particle, gamma ray, and an alpha particle. So we had seen these three distinctions, that alpha is helium in nature, whereas beta is an electron, then gamma are electromagnetic wave. So today's main focus is not on alpha being helium, beta being an electron. How do they penetrate? How are they ionized? What is their behavior in electric and magnetic field as we saw yesterday? And the tracks formed if we use the ion detectors, the radiation detectors. How do these alpha particles, beta particles, and gamma rays behave? Okay. So if I proceed, I'm going to focus mainly on the penetration of matter. We shall come back. So penetration of matter. Alpha particles, beta particles, and gamma rays, they all penetrate through matter. Matter in your O level, sorry, primary, P7 and senior 1. Matter simply means anything that occupies space and has weight. So now we are saying an alpha particle has the lowest penetrating power. You see where I've underlined, where sorry, I've highlighted with a marker. So in your notebooks, this is what you are meant to note. The under penetration, basically, as you revise, what do you need to know clearly? So you are meant to know alpha particles, where you see I have underlined, I've bolded, and using a marker. Please note that one. Alpha particles, they have the low penetrating power. And if the penetrating power is low, even your piece of paper, that paper that you are holding, can easily stop them if they are directed onto it. Yes, so I'm saying this is having a low penetrating power, and then they can either be stopped by a thin sheet of paper. Good. Then we are claiming that they don't travel so far in air because they are easily swallowed, swallowed down by collision. As they try to move, these are radiations. So within space, we expect collision of air molecules with the radiations emitted. So that's why they don't penetrate so fast. Then beta particles, however much they have a more penetrating power, they cannot exceed gamma rays. In other words, we are claiming that the penetrating power of beta is greater than the penetrating power of an alpha, but lower or less than the penetrating power of a gamma. In other words, these are more penetrative than alpha, but less penetrative than gamma. And therefore, if I use a very thin sheet of paper, then this side I'm going to use something that is thick. So we are saying thick paper. On some books, some exams always admire to ask a thin aluminum foil. So alpha, thin sheet of paper, beta, thin aluminum, and gamma, we use lead or concrete, as in concrete. Then for gamma rays, since beta was greater than alpha, meaning that
in progress.
Meaning that the gamma rays are also greater than beta. Then look at this small diagram. I have three particles and I have particles and one ray. I have a beta particle, an alpha particle, and then a gamma ray. How do they penetrate? This is what I was trying to explain above. The penetrating power is low. So when the alpha particles are sent, they meet the first barrier. This is acting as a barrier. But what kind of barrier is this? We are claiming it is a thin sheet of paper. We are seeing that alpha's particle will only stop at this point, whereas beta continues, meaning penetrates through, and then can also not penetrate through the glass or aluminum foil. It stops here. Then these rays, the electromagnetic rays come. For them, they find it easier to penetrate through paper. They find it easier to penetrate through aluminum, but then they are also stopped by concrete. So this last segment is a thin lead, or a thick lead, or lead. Sometimes you can use concrete. Therefore, this diagram is so crucial in your understanding. When you are revising, understand the diagram here. Alpha stops on the first phase, beta stops on the second, then gamma stops exactly at the end. Okay. Now, if you can understand the penetration powers, please, there is somebody whose microphone is on. Can you mute it? We are getting some echoes. Okay. Now let's see the ionization power. Having seen how they matter, how are they ionizing in air? One, what we need to know is the penetration power, the ionizing power, and the tracks formed, and the other three examples that we gave yesterday differences. Now, under ionization of air, we are saying alpha particles, the other side they had a low penetrating power. This side is the opposite. So why the less you penetrate, the higher you get ionizing. In other words, alpha particles have the highest ionizing effect than beta particles. Get to know this. This is highest ionizing effect compared to the beta particle. Then the beta particle, we also have a low or less ionizing power compared to the alpha particle. Then gamma rays, as in gamma rays, they are the poorest ionizers of the three radiations. So when you are focusing, maybe the next question will come and ask you to compare the ionization ranges or the ionization power of air when you are using an alpha particle and a beta particle. Okay. So compare, know that alpha, high ionizing power, beta, less ionizing power. Compared, always making a distinction between two. If you talk of alpha, compare it with beta. If you talk of beta, compare it with the alpha. Because if I say alpha, high ionizing power than beta particles, the beta particles will be less than the alpha particle. Okay. Okay. Now, the funny bit part of it is here. We are talking about the tracks of the three radiations demonstrated in a cloud chamber. Here, finally, we are on. Okay. So, all this you are seeing, I'm trying to underline, will never be asked you at your level. That cloud chamber application and the principle. We shall see the cloud chamber, the Wilson cloud chamber, or the very few that will join A-level and take physics. But now in O-level, what do we focus on? Having given the cloud chamber, how do alpha particles behave? How do beta particles behave? And how are gamma rays going to behave? Observe on these three diagrams very clearly. This is like a wax. This is somehow not strong, meaning it is thin, but these ones are bold enough to be seen. What is asking? Not on our scoop. Okay. Then, so what do we need to focus on is here. Alpha particles, according to this diagram, this is for alpha, this is the beta, and then this is the gamma. Look at the gamma, I'm saying is waxy, the tracks are waxy. Oh, sorry. So we are saying the tracks are waxy. This is the third part. Then in beta, these tracks are the images. Some of you are asking, what are tracks? The track is an image that we shall always see on the screen. So alpha images or alpha particles are short and straight and very bold. So you can see it from here. They are bold enough to be seen, but they are short. However, here this is just elongating it by diagram, but they are already short for me. Then when you look at the beta particles here, this is the source. This is what we call this, what you see like a T, the screen. So we are saying it is because alpha is a good ionizer of air, even beta is an ionizer, but it cannot be as good as beta. Sorry, as good as alpha. Then as lastly, we say that these gamma rays are the worst ionizers. And if they are the worst ionizers, meaning they can never form any good track. They can never form any good track. Then let's see on the beta. Beta particles, we are claiming that for them they are longer and fainter. So why am I saying these are long and not long? We are making a comparison between two things, alpha and beta. Look at alpha tracks and the beta tracks. The beta tracks this side look to be faint, but these are bold. That is the distinction. Then these ones, we claim they are longer than this. If these are short, then you can use a simple English. You say these are taller. But then it does not make sense. Let's say they are longer. Then there's nothing much to compare this. This is like a wax. Those of you know how honeycombs look like. So this is more close to it. So a gamma ray, the track that we always form on the screen are like the combs of honey. That's why I'm saying they are whiskey. Yes, Nabatanzi raising the hand. You can unmute your mic and talk. Nabatanzi, your hand raised. Can you? Solomon, your microphone is not mute. Okay. What is process? Process here we are claiming. Now I said gamma tracks do not need any actual track because they don't ionize the gas. That's why I said these are the worst of ionizers. When the gamma ray is present, then track is formed on the screen. Why did I say that the beta particles are longer than alpha particles? It's so simple. We have to compare the lengths and the energy. Yes, Anisha?
Actually, I'm not understanding anything.
Yes. From where?
From what? Penetration of matter. I'm not understanding anything.
Do you see this diagram? No, wait. This diagram. Are you seeing where my cursor is?
Yes.
This is an alpha particle, right? This symbol represents alpha. Only going to stop on the first phase. So the first phase represents a sheet of paper that is very thin. So only alpha can be stopped by a thin paper, but beta and gamma will continue to penetrate. That's why we are saying that the penetration power of alpha is smaller or less than beta. That's why above I said the low penetrating power, and if the penetrating power is small or low, then a thin sheet of paper can easily stop it. But if it exceeds, like a beta, it cannot be stopped. It is just going to penetrate and pass through. However much is also going to be stopped by aluminium foil. When it reaches the aluminium block, it stops. When you observe on these three diagrams, look at this small line. It's as if I do it very faint. right? This one is more black, thicker. And this one is like a concrete wall, like that that I'm seeing behind. So this is the concrete. You get the point. Now, if I have gamma
Yes.
rays, they are going to be stopped by concrete. Then, meaning they can easily pass through aluminium. Aluminium, an example of aluminium are those iron sheets that we always use at home. Beta particles cannot pass through the iron sheet because they are made of aluminium. And they can pass through your paper. Is it okay? So that is more of penetration. And that is another difference apart from the other three in the table. Now then ionizing energy or ionization in air. You can now remove your microphone. Okay. So ionizing energy or ionization of air. I'm claiming that alpha high ionized, meaning they are good ionizers. They are heavy. They can carry charge compared with beta, but good. Then beta are less microphone. There are a lot of problems to have. I'm not going to ask you to mute the microphones because I can do it, but these are the things that you can learn. I'm sorry. Okay, you only put on your mic if you want. Then we are claiming beta particle. Comparison between beta and the alpha. On the above diagram said alpha, mean that they have high ionization energy. Then beta particles have a high penetrating power compared to alpha, meaning that the ionization power is small. Because you cannot have two cases at the same time. You cannot penetrate very fast and then ionize very fast. You know, you need to do one at a time. Then for gamma, don't always focus much on it. The way you see it penetrates very fast, it has nothing to do with ionization. It is the poorest ionization. Why? Because this is not a particle, but it is a ray. And in other words, these are magnetic waves. Is it okay? Yes. I can see all of you. Sophia, stop eating in my class. So then for tracks, I said tracks, look at the diagram, the shape, where I've underlined and bolded. The thing. That's what you need to note down in your books. Those who have pens in their hands and the notebooks alongside themselves, they're meant to note these things that I've bolded and highlighted. An alpha particle, short, straight, and bold tracks. Then beta particles, they are long, they are not straight. That is another thing that is not included here. And they are fainter. Why am I saying fainter? They are fainter because I'm making a comparison between beta or beta particle and alpha particle. Then gamma, these ones, as we said, they are bad ionizers, and therefore they don't leave any track, meaning they don't form any image. But should it happen that there is an image formed by gamma ray, then it is like a wax. Sorry, like wax waves. That's why you say they are wavy tracks for this treatment. wave works. In other words, that is only and only if the gamma rays are present. Okay. Anisha, your hand is still raised. Do you have any question?
No.
Okay. Now look at this. But if you have any questions, you may ask. Before I go for nuclear energy. But today I had to focus on three things: tracks, ionization, and penetration. If you understand those three, then you are able to distinguish the radioactive particles emitted when radioactivity occurs. So all this we are doing before I go for nuclear energy, it is all about radiation, radioactivity, as we saw yesterday. As our second subtopic was radioactivity here. This was our second topic, subtopic radioactivity. And for those who are present and would have joined us yesterday late, all the work that we discussed yesterday is on the YouTube. I shared with you the channel, the link. You can access and watch again, connect and follow. Okay. So nuclear energy. So the more chemistry now comes in here. Okay, nuclear energy. Now here we are going to focus on an atom, its nucleus. It's either splitting or placing. We said you remove your video. Okay, nuclear energy. Nuclear energy has things that we are going to focus on: to fuse and to fizz. To fuse and to what? And to fizz. You see that your hand is up. Let me mute you all and I see. Okay, we proceed. Nuclear fusion and nuclear fission. The first is fizzing, Fi, then the other will be fusing, Fu. To fizz means to split. To fuse means to combine. Okay, so here we are saying we are going to split a heavy atom into a light or lighter nuclei. So I'm going to just draw some small thing. So I'm assuming I have an atom which is big, but this atom is going to split into two. So this is what we call fizzing. Nuclear fission, you split this bigger and you get two small or lighter nuclei. However, the mass of this nuclei or the mass of this atom is always equal, almost roughly equal to the mass of this atom. And in other words, we shall claim that these two split atoms shall be called daughters. So this is a parent, this is a daughter. And then whenever we split, we always have what we call excess energy.
Master, you are not audible, Master. Master, be audible.
Wanji? Yes, Mr. Das? Anisha, you can see?
Me, I can see.
Okay. So I'm saying this is big, it splits to form two, and then not everything that has split is going to be utilized. There will be excess energy. And in this case, we shall call these products the daughters or the fragments. Like when you get a big stone and you hit it, it forms small pieces. The small pieces of stone that we form are called the fragments. But remember, you use the energy. That is excess energy that we are going to see. According to Einstein, he's going to give us a correct definition of the formula. And then this side, we shall always find that this energy is always equal to m, which is the mass of each times the speed, then squared. So that is according to Einstein's energy. Then for this atom to split, then it must suffer what we call a neutron. It suffers a neutron. So it is the presence of a neutron and the atom that are going to help us split to get these two daughters. Now this daughter itself will have a neutron, and this daughter also will also have a neutron. So in this energy that we always account for, we account for the excess two neutrons produced after splitting. So look at the statement here. I'm saying that nuclear fusion is the splitting of the nucleus of heavy atoms like uranium. When uranium splits, it gives us the daughters. Then into two lighter nuclei of roughly equal mass. And then we are saying the process nuclear fusion can be started by bombardment of heavy unstable nuclei with a neutron. That's what I was trying to write here. This is very heavy and is unstable and is a nuclei. But to bombard it or to break it, then I need to use a neutron. So bombarding a heavy unstable nuclei with a neutron is the same as somebody defining nuclear fission, fusing, not fusing. Then these two lighter products of nuclear fission are called fragments. These two daughters, these are what we call the fission fragments or the daughters. So we shall see it in an example there down. And the energy I was trying to say according to Einstein is here. The energy I was referring, the excess energy that is always released according to Einstein, and we always call it the mass defect. So M is mass defect. C is the speed of light in air, which is a standard value, 3 exponent 8 meters per second, but the mass can change depending on what we are using. Then we are claiming that neutrons, so the fission neutrons ensure the community so they ensure the continuity of nuclear fusion indefinitely, resulting in two chain reaction. Now look here. When these splits form this first daughter and the second daughter, even this first daughter becomes unstable in its own because it is now independent. And the second daughter becomes unstable because it's independent. Now these two, this can make the chain continue, and as well, the second daughter can make the chain to continue. Why? They are all unstable, and mean that the process will never stop. If you follow this diagram here, the chain reaction, I have a neutron. I have a neutron bombarded with uranium, then it forms two daughters. The first daughter is here, the second daughter is here. But because these two daughters also make it unstable, it continues. The first daughter gives you another reaction. The second daughter gives you another reaction. You find out that the system will not stop until it reduces to the smallest stable particles that can be produced. Like look at this equation above. I don't know if it is so clear to you. This is uranium 23592 bombards with a neutron. The first daughter is barium, the second daughter is krypton. So these are the fragments I was talking about. But each daughter has its own neutron that makes it continue split. So when you have to balance this equation, barium is 144, krypton is 90, and then two excess neutrons are produced after splitting. This is the excess energy I was trying to mean according to Einstein. Now, when you look at this equation to balance this, sometimes I can give it and then I ask you the value here, which is 56, and I put unknown y, and so you equate what is on top. So it implies that 2, we are yet to stop, so don't worry. So when I add this on top, plus this smaller one for a neutron, this is a chain reaction symbol, meaning that this is the left hand. What is on the left must be equal to what is on the right. So this is the left. I have 235 plus 1, that is 236. So 2, 3, 6 must be equal to 144 plus 90, 1, 4, 4, 1, 4 plus 90. Now you can observe that it is not balancing because this is going to give you 2, 3, 4. To balance it, I need extra energy. So this extra energy is saying that I'm having 2 neutrons. So this 2 is going to multiply with the 1 on top and it becomes 2. So when I add this 2 here, it becomes 2, 3, 6. This 2 also multiply with the 0, it becomes 0 plus 36 on the lower part plus 56 gives you 92, which is the same value of uranium. Okay. Big stop there. Let me see what is in your charts. Okay. Any question? No question? No questions?
No questions.
Okay. Wish you the best.
Eh,
Na ye mwekume.
Hey, first, next week are we having Mr. Baker's lesson?
BK told me he's going to give those of West Africa the notes, but not the lesson.
And to some of us, I never brought the geography books.
But West Africa is not geography.
No, like geography notes.
Okay.
But some of us don't have the books.
Okay, wish you the best. It is raining this side. Right.
Tegeera.
Okay.